So today we're joined by Dr. Mohsen Amjadian, an incoming assistant professor in the Department of Civil Engineering at the University of Texas, Rio Grande Valley, starting this coming fall. And prior, he received his PhD in structural engineering from the City University of New York, where he pursued his research as a postdoctoral fellow in the Civil Engineering Department and also served as an adjunct lecturer. His research focuses on modeling, designing, and testing smart structural materials and control systems to enhance the structural performance of civil structures subjected to natural hazards. He's also a regular reviewer for several top journals in the fields of civil and mechanical engineering, and received the 2016 Outstanding Reviewer Award from the Journal of Bridge Engineering of ASCE, where he's currently a member of the Early Career Editorial Board. So with that, Dr. Amjadian, why don't you take it away?
Thank you, John. Thank you so much. Hello, everyone. As John said, my name is Mohsen Amjadian. So today I present the work and the project we have with the C2S Smart. First, I want to thank C2S Smart team to give us this opportunity to work on this interesting project. This project is about developing a harvesting electric energy device to power sensor installed on highway bridges specifically. The PI of this project is Professor Anil Agrawal, my advisor, and Professor Hani Nassif and I are co-PI of this project. So let me start going forward. So this presentation includes 5 chapters, 5 sections. Introduction, theory, and basic concept, design, fabrication, and testing of a proof of the concept prototype. This part of these 2 parts have been investigated in phase 1 of this project. In the phase 2 project, we are currently working on developing a high power density electromagnetic energy harvester, which is currently we work on it, and hopefully we hope to complete it by next year spring. And finally, chapter 5, I conclude the work. So let me discuss the background and motivation of the research. The number of vehicles in the US has increased very much over the past few decades. And the highway statistics shows that average daily vehicle miles traveled in the US is about more than 5 billion. And this represents a very large amount of kinetic energy that embedded in the and unused in national transportation network in the US. So this energy can be harvested to power wireless sensors in the solid on bridges. This kinetic energy can be converted to electrical energy. So we can use that electrical energy to power wireless sensors, which are usually used to monitor the structures, integrity of structures. And this also can help to reduce some dependence on the fossil fuel drive energy. So here in this figure, you can see typical wireless sensor like acceleration sensor here, and or a strain sensor. Let me use the laser. Yeah, and a strain sensor. So these are typical. Sorry, I have to change. Yeah, these are typical sensors are installed on bridges to monitor their behavior. And these sensors usually need a couple of small batteries for the operation. But these batteries have short life, and when we compare it to the lifespan of the bridge, so we usually have to change them. In this research, we are looking for we want to model, design, and test electromagnetic energy harvester, which can generate a high output electric power. We prefer the electric power be above 0.5 watt at the resonant at the specific frequency, which is resonant frequency. And this amount of power is enough to drive conventional wireless sensor, which are used for structures monitoring bridges. To reduce the size of, and the second objective is to reduce the size of the device and increase its electric power, or let's say energy density, by optimizing the arrangement of the magnets in this device, and which can be planar or linear array. I will discuss these terms later. And to amplify the magnetic field of the permanent magnet, and also the harvested electric power. And this leads to cause the strengthening of the electromechanical coupling between mechanical and electrical domain in the device, which, as I said, cause increase in the harvested electric power. Okay, so before I start the theory and concept of the device we developed, let me go over the component of a self-power bridge monitoring system. So the source of all these the source is excitation in the bridge, which is caused by traffic, which cause vibration of the bridge, or any other type of transportation infrastructure. So the objective here is to harvest this energy, this kinetic energy, using energy harvester. Here we focus on electromagnetic based energy harvester, which in simplified form you can see here includes a magnet, vibrates with relative to a copper coil. And the relative motion, the magnets with respect to the coil induce electric current inside the coil. And our objective is to harvest that electrical current or voltage in the coil. Because the nature of the motion of the bridge is harmonic, is a harmonic vibration, and the motion of the relative motion of the magnet and the coil, they also harmonic. So the output is alternating current or alternating voltage. So another component of this system is a converter, which converts this alternating current to a DC current, which usually is based on a full bridge rectifier. For example, you can see we have a harmonic voltage. By this rectifier, we can convert it to a DC and quite a stable DC voltage or current. And sometimes we need to amplify that output DC voltage or current. So we can also use a DC to DC converter. This is another component of a such system. And after that, we can store the power in, for example, rechargeable battery. And we can connect that rechargeable battery, which is continuously charged by the motion, by the vibration of the bridge, to a sensor. We connect that battery to a sensor, so we can say that the monitoring system is self-powered. So vibration causes electric power in the system, and we have a self-powered monitoring system. And we can use that sensor to measure the response of the bridge, and this creates a closed loop. We don't need any external power to drive the monitoring system here. Of course, this is a perfect scenario. In reality, things things are different, and not everything is perfect. But this is the objective of this research, and we hope we get to a good position by finishing this project. In this part, or today for this research, I focus on the development of or design of the device, electromagnetic device, and the interaction between the magnetic source and the coil. Chapter 2 is about theory and basic concept and of the device, in which we develop an electromagnetic energy harvester with planar array of a permanent magnet. So this figure shows the configuration of the device we developed. And this shows the analytical model. So here, you can see this is the left magnetic array. This is right magnetic array. So they are two magnetic array. And this is the coil. The coil is attached to a damper and a spring system, which they are attached to the base, just like the permanent, just like magnetic arrays, left and right. And the base here actually represent the bridge, for example, and the bridge here, for example, move with this this excitation function, which we can represent it by harmonic motion here. And here in this figure, B, you can see the plane of the magnetic array, includes a couple of small magnets. The arrangement of these magnets are important. The gap, the air gap between these magnets are important, which we discuss the change in these parameters later. But you have to, you might remember Faraday law of inductions. The motion of the coil with respect to the magnets cause a change in the magnetic flux of the magnets, and that, based on Faraday law, induce a current inside the coil, or let's say voltage. We can install a circuit, a harvesting part of a harvesting circuit to this coil, to harvest the electric power from the voltage electromotive force induced in the coil. So we represent this harvesting circuit. In a simple case, we represent it with one load, one resistance. So the amount of this resistance also is another important factor of this this model. And also here we have a tip mass. This tip mass can be attached to the coil because maybe the mass of the coil is not enough, so we can attach a tip mass to the coil. So that helps us to also vary the frequency of the system to make sure that frequency is close enough to the frequency of the external excitation, which is, let's say, fundamental frequency of the bridge. And that causes resonance in the system, which helps to increase the amplitude of vibration and also amplitude of the increasing the voltage or electric power. So yeah, this is the general view on the model we have. So we have to simplify this model using electromechanical model, and this figure shows the electromechanical model of that the device we have. As I said, includes a harmonic base excitation, a mass, and a circuit. which is alternating current RL circuit, a resistant and inductor circuit. The coil here can be represented by a resistor and inductor. So they are in series, and we can find the resistance of the resistor with this equation, which is typical equation in electrical engineering, and also induction of the coil depending on the geometry of the coil, which here is a square. The plane of the coil is a square, so we can use this formula. And RL, as I said, it represents the resistance of the harvesting circuit, which is called the load here. And we have to take 4 steps to develop or set up the governing equation. The first step is to find the magnetic flux density vector of the magnets in the arrays. And the second step is to find and to develop analytical model for the coil, and then magnetic interaction between the magnets and the coil, moving coil. And finally, we can set up the electromechanical governing equations, which couples the mechanical domain to electrical domain. So, so the first step is to set up the permanent magnets arrangement and find the magnetic flux density. So as I said, the arrangement of the magnets based on the based on the direction of the poles is an important feature of the device. This can significantly affect the interaction with the coil when the coil moves with respect to them. So in this study, we consider 4 different types of planar arrays, which I show them here. The first array is a uniform array, and the poles are uniform. And the second array is X-linear alternating array. So you have to remember, this is the direction of the motion of the coil. So in array 2, the poles alternately change in X direction. In array 3, which we call it Y-linear alternating, the alternating change happens along, in the poles of the magnets happen along Y direction, in this direction. And the last one is planar alternating, checker, which I showed here. And so you have to remember that the magnetic, these 2 array 2 and array 3, they have same magnetic field, but the magnetic interaction with the coil is different, can be different. And this is because of the specific arrangement they have. Array 2 is obtained by 90-degree rotation of the array. Array 3 is obtained by 90-degree rotation of array 2. But later you can see they have different effects on harvesting electric power we can get from the device. Okay, so now how we can model a magnet. From electromagnetism, we can say that magnetic flux density vector of a single magnet can be calculated using equivalent current model. In this model, each magnet can be represented or reduced the distribution of equivalent bond surface. So the magnetization in the magnet can be represented by a current, a surface current circulating over the surface of the magnet. And this help us to use Maxwell equation, the magnetostatic form, to write this equation in form of surface integral to find the magnetic flux density of that cuboidal magnet. And if we take integration over the surface of the magnet, then, for example, if this is the origin, then we can find the magnetic flux density vector in a point in a space using this function, which this parameter or this function bx, by, bz can be defined this way. And when we find magnetic flux density for each magnet, if we sum all the magnetic field, then we can get the magnetic flux density all the two PMs array, so which can be obtained using this equation. Okay, so the next step is to develop analytical model analytical model for the coil, which can help us to find mathematically how the moving coil interact with the permanent magnets. So the magnetic field of a single layer coil, a core coil. So you have to remember, iron core coil is different with a core coil. Iron core coil is has very complex behavior, and because of the iron core it has, but is very difficult to analytically work on it. So here we focus on only a core coil here. So a core coil can be each layer of a multi-layer a core coil can be represented by one equivalent permanent magnet. So you have to so when each layer is represented by one permanent magnet, in the previous slide we found the magnetic flux density of permanent magnet. Then we can use that equation, that function, to find the magnetic flux density of each layer. Then we can add all the magnetic flux density of all the layers to find the total magnetic flux density of the coil, which can be obtained using this equation. And here you can see the coil, we assume it's a is a square, same dimension, and this also shows the direction of the induced current in the coil that cause magnetization in the coil, and the equivalent magnetization vector of the equivalent permanent magnet at each layer can be obtained using this equation. You can see here this magnetization depends on the current induced in the coil. And because current in the device is variable, so this magnetization also is variable by time. And yeah, here we show the number of turn in z direction and number of turn in vertical in x direction, and so on. So this is the way we model coil. Simplify, if I want to put it in a simplified word, I can say we can represent it by equivalent permanent magnets. And we already developed a required equation for permanent magnets field. We can use those equation or formula. So now how we can find or develop the magnetic interaction between the coil and between moving coil and the magnets. So this interaction can be represented by Lorentz force law in electromagnetism. So let's say for one layer in the coil, we have this current, surface current circulating in that layer, and it has a magnetic interaction with the magnetic field of one of the magnets in the array. The magnetic force interaction using Lorentz force law can be obtained using this surface integral. If we do the integration later, we can find this equation in terms of the dimension and magnetic dimension of the coil and dimension of the magnets, and also the their magnetization vectors, which here are represented by BR. This is for the coil, and this is for that specific magnet. And V here shows the volume of the equivalent cubic magnet in the coil, and that also shows the aspect ratio of the coil. Sorry. And finally, we can sum all these forces, which shows the magnetic interaction between each layer of the coil and each magnet, to get this equation or this formula, which shows us the total force applied to the coil because of its motion with respect to the arrays. And FC has a three components. In this study, because the motion is in X direction, we have only this component. And because of symmetry, FCY and FCZ, they are 0. Okay, so now we have all the tools and all the formula we need. Now we can develop the electromechanical governing equation, the equation that governs the motion, the interaction of the moving coil with respect to the magnets. So this equation, many of you know that, is a single degree of freedom vibration, represent the vibration of single degree of freedom system, which shows the motion of the coil. And this is the force applied to the coil because of the motion, its motion with respect to magnetic field. And this equation also represents the circulation of the induced current inside the coil. They are coupled. The magnetic interaction force, FCX, can be showed using this equation. Can be showed or expressed in state in terms of the induced eddy current, induced electric current in the coil. This KF is called electromechanical coupling coefficient, which changes by time, is a time varying variable or parameter here. This is very important parameter because couples the electrical domain of the system to mechanical domain, and it is important to obtain this or calculate that. But the way we calculate this coefficient here is that we assume at each time step the induced eddy current is equal to -1. Then for each time step, we can say that KF is equal to the magnetic force between the coil and the magnets when the current is equal to -1. And using that, we can find KF. Then we multiply KF with the correct value of current, then we can get FCX. But this FCX we can calculate using the formula we developed in the previous slides. So alternatively, we can find FCX using this equation, which is Lorentz force for a current carrying wire. And if we manipulate that a little and change a little, then we can find that KF is this equation. Okay. But you can see this is a line integration, which has to be taken over the length of the coil wire, which is very complicated integration. But you have to remember we used the previous equation we developed for FSC, so we don't need to write or solve this integral. And yeah, so this is an important point. In many of papers we reviewed, I saw that many researchers assume that KF is constant. The reason is that because because analytically it's very difficult to find KF because it depends on the geometry. And as I said, taking this integral is very complicated. So many, by some assumption, they assume KF is constant. And doesn't change with time. But this is simplification and sometimes can cause error in estimation of the harvested electric power. But in this study, KF, because we have accurate equations or formula, we can find KF accurately, and we verified that with finite element model. The electromotive voltage, which is the voltage force, which is voltage induced in the circuit, can be calculated using this equation, which is based on Faraday law of induction. And if you compare this integration with this integral, you can see there is this relationship between velocity and voltage and Kf. And you can see Kf couples electrical domain to the mechanical domain, and it's very important parameter in studying electromagnetic energy harvesting systems. So we know the current can be represented in terms of voltage and later velocity, and we can remove the second equation by putting the equivalent value of current. Then we get this equation, and in the first equation. So you can here zeta S represent the critical damping ratio in the system, which is called mechanical damping. Actually, it's because of mechanical damping in the system. And here you can see magnetic interaction between the coil and the magnets cause electrical damping in the system. Increase the electrical damping in the system, and this is actually in literature reviews called eddy current damping. And omega S is the natural superfrequency of the system. And you can this equation is nonlinear because this term, as I said, Kf is nonlinear. So there is no analytical solution to this. Even this term is harmonic because Kf is nonlinear. So we solve this using numerical function in or method in Simulink. Then we obtain the instantaneous power, which is consumed by the load, or if you remember, I said harvesting circuit, or here we call load. And the objective here is to use average electrical power as an index to investigate the performance of the system. So our objective is to calculate this parameter in the system. If we assume, let's say, if we assume Kf is constant, then we can do then everything will be analytical. We can get analytical solution for displacement here, and then we can optimize the resistance of the harvesting circuit. And here you can see, based on the work done by Stefan, this is the optimized resistance of the circuit, which here you can see is larger than RC, which is the resistance of the coil. But in reality, Kf is not constant. Later, based on numerical result we got, we will get, you can see our optimized RL is less than RC, is not larger than RC. This is just for the case when Kf is constant. Okay, so before we go forward and do parametric analysis, we did a finite element verification on the device for these parameters. Because I don't have much time, I want to go forward quickly. So we did a parametric, we developed a simple finite element model, including 2 permanent magnets and the coil in a console, which is finite element software. And we compared it with the same analytical model. We compared the result with the same analytical model. And here you can see the force obtained from the finite element software match very well the force obtained from the analytical model. So this proved the accuracy of the analytical equation we developed in the previous slides. So let me, here also you can see KF, variation of KF by time. And you can see at very large displacement, when this is KF with respect to displacement of the coil. You can see at very large displacement, these tend to be 0, which makes sense because at large displacement, the electrical domain and mechanical domain are decoupled, so KF must be 0. And of course, in KF, when velocity is maximum at the center, is 0. And yeah, so we did a parametric analysis. So this is the model we have. We have a lot of parameters here, but the parameter here we used for this specific parametric analysis includes the magnitude of the bridge vibration acceleration here, and also frequency. We assume the frequency of the vibration is constant, 3.5, but we assume the device is in resonance with the excitation, which is 3.5 hertz. And also the another variable was the resistance of the load, which is harvesting circuit. And of course, we did this parametric analysis for 4 different arrays of magnet. Here you can see the vertical axis shows the average electrical power harvested from the system. And here you can see array 2 caused the largest amount of electrical power in the system. So we have to use this array to finalize the design of the device. And here, if you remember, I told you this array is obtained by 90-degree rotation of this array. And you can see how much is how much weak is its interaction with the coil. Very small amount of electric power here. And for example, for array 2, the maximum electrical power we can harvest from the system is obtained when the electrical resistance of the harvested circuit is 25% of the coil, resistance of the coil, which is almost 0.5 watt, which is close enough to what we expected. But we have to remember this is this high amount of power is obtained for 0.1 G vibration in the bridge, which is not very common. Usually vibration of the bridge cause very smaller amount of acceleration. But anyway, for that is possible, but it's not common. Okay, so this was the result of analytical model, but you please also remember this arrangement. Okay, we develop a experimental model, so we use this arrangement. I will discuss why we finally decide to use this arrangement, not this arrangement, optimized arrangement. But let me go forward and to design, fabrication, and testing of a proof of concept prototype. So we designed the prototype based on the analytical model we developed. Here you can see the CAD design of the device. Here are 2 arrangements of the magnets. And this is the coil. And this is a base plate, which is fixed to the bridge, for example, or the shaker, where we excite the system with external excitation. And this is a moving mass, or we can also connect the tip mass to this part. And these are springs, and also mechanical damping is embedded, is hidden in the system. And these are different view of the device. And this is the fabrication of the device in the lab. So I have to mention that we had a problem with developing or setting up these tests in lab because of over a couple of months ago because of pandemic in college. So we decided to move all the tools or facility we have to my own apartment, including computer, data logger, and the shaker. So to set up the test in my own apartment. So these pictures are from my own apartment. So here you see the device. These are magnetic array. These are springs. We also installed the accelerometer here to measure the acceleration of the base. And that is the coil, and that is also tip mass, and this is a shaker. You have to remember this shaker is not very a perfect shaker, is actually actuator because of its performance limitation. We couldn't really produce a perfect harmonic load or motion, which I discussed that later. And we couldn't use this strong this array which caused the highest amount of electrical power. Why? Because first let me say we use 25 small half-inch size cubic permanent magnets. Okay, when we want to attach them according to this array, it's very difficult to attach them by hand. You know. So it was difficult for me to do it. So I decided to put the magnets in this array. Why? Because this way they are statically in equilibrium. They easily attach to each other, and they are not. I don't need any external force or glue to attach them to each other. You know, they are by default or by nature are attached to each other because of their equilibrium, force equilibrium. So we use this. Just to set up the test and measure the voltage. It's just prototype. And yeah, we use a data logger. We measure the output voltage by computer, and we also measure the accelerometer when we use the shaker to input the excitation. And you have to remember, we didn't use any resistance here as a to represent the harvesting circuit. We assume is 0. So we directly measure the voltage induced in the coil. And here you can see the arrangement of the permanent magnet, and here you can see the size of the coil. And you have to remember this arrangement must be in opposite direction to make sure they create a continuous and a straight magnetic field, which is strong enough when the coil is exposed to that magnetic field. So here you can, if I okay, so I don't know how can I. Yeah, okay, sorry. So here you can see how the tip mass is shaking, and that is the coil based on the frequency of the vibration. So we did 5 tests for this arrangement. So from 1 Hertz to 3 Hertz. So here, as I said, because shaker is not perfect, we couldn't produce perfect harmonic motion. So here, for example, you can see power spectral density of the 3 of the motions. For motion number 3, you can see the highest amount of power is obtained at 2.3 Hertz. For the fourth one is 2.4, and the last one is 3. So 3 was the maximum frequency that we were able to get from the device because of the limitation of the device. So these are the output voltage after we filtered the output using a band pass filter. And you can see the highest amount of voltage is in the case of this vibration, this excitation, which is 334 microvolt. So this voltage is very small, but this is the beginning. This is the initial result. So in the next step, I am going to decrease the stiffness by removing these shafts. So then the system will be more flexible, so I can reduce the frequency. And I think that helps to make sure the frequency of the system can be matched with the frequency of the shaker. You see, this is because of the limitation of the shaker we have. And the next step, which we hope to do it maybe in 2 weeks, is to put the modified version of the device on a bridge in Manhattan, which is in New York, which is a Triborough Bridge. Professor Agarwal is working on it, and he's going to get permission to install the device there. We put the modified version of this device. And we want to put the device on a walkway of the bridge. So yeah, so I'm done, but I have some more slides which represent the modified version of this device for the next phase of the study. In this, actually, we did some parametric analysis, and we published the result in a conference, SPI conference, last spring. Because this version actually has a smaller volume, you can hear. Let me show you actually the amount of power we get. You see how much power we can get is very large. So we hope to use this version of the device to increase the power density. But what we have right now actually is prototype of the device, which I showed you here. And yeah, so this is not the final design. We final the design in the next phase of the study. Thank you so much.
Okay, great. Thank you very much, Professor Amjadian. And if you send me the conference paper you referenced, I can send it to the participants at the end of today.
Sure, sure. I will send to you.
I'd like to open this up to the audience for questions. As I mentioned, you can feel free to use the Q&A button, or you can raise your hand and I'll unmute you. You can ask your questions directly. I think I'll start one off. So you spoke a lot about developing the prototype so far. Can you talk a little bit more about any challenges you anticipate would when implementing this research on the actual infrastructure that might be different than the lab conditions?
Yeah, that's a very good question. Thank you. So yeah, I think one problem is the matching the frequency of the bridge with this device. The good way we can do it is to measure the frequency of different type of bridges in for example, New York, then find which bridge has the closest frequency to the system, then install the device on that bridge. But I think Professor Agarwal is responsible for that part. I can do that. But I think for this one, we just stick to Triborough Bridge, if I remember the name. So I'm not sure about the frequency of that bridge. So I have to go there and measure the frequency using that accelerometer. And probably I will be able to modify the frequency of the device so that the device frequency be close enough to the bridge. But I don't guarantee, because right now I have no idea. Yeah.
Sure. And so when you were, I apologize if you brought this up in your introduction, but as far as you know, has this type of research been implemented in field before, or is this kind of
there are a lot of work have done beyond the harvesting energy from vibration, but the difference, the work we have is the first, the analytical we developed, is most accurate analytical model. I didn't see any paper that can model coil the way we did. And as I said, the electromechanical coupling coefficient is a time varying variable. In many studies, they assume it's constant. So the good thing is our analytical model is accurate, and this analytical model can be used to modify the design. Okay, so we get more accurate result. And another important thing is we are looking for very high amount of electrical power. So in many of the study, they want to use a smaller, because the size of devices they use are small. So they limit the output power. But what I can tell you, yeah, there are a lot of different type of devices, magnetic, piezoelectric. So this is ongoing research, you know.
Okay, so one last question here. What would an implementation win look like? So in terms of how many harvesters producing how much energy and enough to power what? What's the highest upside that you can imagine with an implementation on?
Yeah, so as I say in objective, our objective to design the device to get at least 0.5 watt electric power. So I think this power, based on our experience and my discussion with Portugal, this power will be enough for driving or powering many of conventional wireless sensors. But of course, this is one step. The designing the device is one step. The other steps are developing other component of the system, like AC to DC converter, DC amplifier. You know, those are also other components. But here we just merely focus on this part of the system. And our objective, as I say, is to reduce the size and increase the output electric power to 0.5 watt. Yeah.
Okay, if there are no more questions, with that, Professor Amjadian, thank you so much for joining us today, and thank you to all attendees. Before we leave, I just want to acknowledge this project and the CT Smart Center is funded partially by US DOT. If you enjoyed this webinar, definitely follow the CT Smart Center on Twitter, join our LinkedIn group, now our company page actually, excuse me, and our mailing list. We hope to see you at another one of these soon.